Okay, so we start from here now. Remember, this was the end of the last class, and so just we write down the composition here, and this is sodium 0.57, Ca2, Mg 3.7, aluminium 1.3, aluminium 1.87, and silicon 6.13, 422 OH So that's the composition of the amphibole here. And if we found out the composition of the amphibole, and now let's find out what is the product, what are the mole fraction, mole percentages of the product phases. Yeah. So we first look at, say for example, if we look at dioxide, CaMgSi2, CaMgSi2O6, and by the same method we can now write, so 2 into 0.03 or 0.03 into 2 plus 0.07 into 2 plus 0.5 into 1 plus 0.4 into 0, because there is no dioxide here. And this would then add up to 0.06, 0.14, 0.5 and 0. So CaMgSi2O6 would be 0.7, if that is right. Yes, it's 0.7. Right? Then we have MgSiO3, and this again you can see it's 0.03 into 3, 0.03 into 3 plus 0.07 into 0.07 into 3, yes, plus 0.5 into 1, no, 0.3 and plus 0.4 into 3. So this should be 0.09, 0.21, 1.5 and 1.2. So we have 3.7, 3.91 and no, 1.5 plus 1.2.
2.7.
Huh?
2.7 altogether it will be 3.
3. It should be 1.5, 1.2, 2.7, 2.91,
Yeah.
and this should be equal to 3. Then we have NaAlSi3O8. If we do that, then 0.03 into 0, because there is no albite in this. Then you have 0.07 into 1 plus 0.5 into 1 plus next one does not have it, so 0.4 into 0, and this should give you 0.57. And then you have CaL2Si2O8, and so it will be 0.03 into 0 plus 0.07 into 0 plus 0.5 into 1 plus 0.4 into 2, and this should be equal to, this is 0, this is 0, so this is 0.5 and this is 0.8, right?
0.13.
1.3, huh? So this should be 1.3. And finally, we come to SiO2. So finally we come to SiO2, and this, remember, we have SiO2 on this side and we have SiO2 on this side. So if we take this as positive, then this should be negative. So if I take tremolite, then it is 0.03 into 1, 0.03 into 1, if this is positive, then the rest of it should be negative because it is to the left. So then you will have 0.07 into 3 minus 0.5 into 4, 0.5 into 4 minus 0.4 into 1, and this should be equal to 0.03 minus 0.21 plus 2.0 plus 0.4. Is that right? Is it right? Yeah. So this should be equal to 0.03 minus 2.61, right? So this should be equal to minus 2.58. So this is what it should be eventually. You please check out the calculation, it should balance at the end. So now the reaction that we have is, I don't know where to write it. I will erase this reactions because we now know it. So we'll erase these reactions and we'll write the equation. So now, I will repeat again. Na.57, Ca2, Mg 3.7, Al 1.3, Al 1.87, silicon 6.13, O22, OH whole twice, plus, now this is minus 2.58, so this should be plus 2.58 SiO2. Right? So this should be 2.58 SiO2, and this should be equal to 0.7 CaMg Si2O6 plus 3 MgSiO3 plus 0.57 NaAlSi3O8 plus 1.3 CaAl2Si2O8. Is that right? Yes. Plus H2. So this is the amphibolite gaseous Hamden quartz that breaks down into this product. Now, if you see this one, then what is the albite percentage of this plagioclase? Albite percentage of this will be 0.57 divided by 0.57 plus 1.3. Can you calculate how much it will be?
30%. 30.
30%. So albite percentage would be about 30. So this would be the composition of the plagioclase. And as you can see, you have albite, oligoclase, andesine. Albite is 0 to 10 sodium content. Oligoclase is, in albite content is 0 to 10 for, in albite, anorthite content is 0 to 10. And 10 to 30 is the anorthite content of oligoclase. And andesine is 30 to 50. So now you have at the borderline, this will be the condition, this will be the point composition of the plagioclase. And here it is the proportion of OPX. So mole percentage of OPX, this will be equal to 3 divided by 3 plus 0.7. So can you do that? 3 divided by 3.7.
81.
81%. So 81%. So you produce a 2-pyroxene assemblage, clinopyroxene, orthopyroxene, and you produce a plagioclase. So in that, the mole percentage of orthopyroxene is 81%, and the plagioclase composition, albite percentage is 30. Albite percentage is 30. So the anorthite content is 70. Right? Now you must remember from the reactions I wrote, from the way the reactions were written, if you have Scherbakite, say for example, if your amphibole is Scherbakite rich, it will produce only anorthite, the last reaction. So if you only have Scherbakite, high percentage of Scherbakite, it will break down to more anorthite molecule. But if you have Pargasite, then your albite to anorthite ratio is 1:1, which is around 50%. So it would be the plagioclase composition and the molar proportion of orthopyroxene and clinopyroxene should depend on the proportion of the dominant component that make up your hornblende, or the ratio of Pargasite and Scherbakite in your original hornblende. Because adenite and tremolite contributes very little. So the dominant 90% of this hornblende is constituted by Pargasite and Scherbakite. So their ratio will dominantly contribute to the proportion of OPXs to CPX in your slide, and composition of plagioclase in your slide, in the granulite facies rock. It will be dominated by this. So that is how you can see. There is now a little question here. There are several questions here. And this is an important critic of the metamorphic facies diagram. Let me be very clear about it. And those lines that are drawn on the metamorphic facies diagram indicating facies boundaries, the actual nature of it. So here you see you have a system Na2O, CaO, MgO, SiO2, H2. This is your system. So this is I'm ignoring at the moment iron. At the moment I'm ignoring iron because we have done all the calculation with magnesium. So we have Na2O, CaO, MgO, no, I've forgotten. MgO, Al2O3, SiO2 and H2. Right? This is your component. So we have component here of this reaction equilibrium is equal to 6. And what is the number of phases here? And what are the number of phases? Now this is important. Hornblende, 1 phase. Quartz, 2 phase. Diopside, 3. Enstatite, 4. And plagioclase. These are not 2 different phases. This is the same phase. So 1, 2, 3, 4, 5. And so 5 solid phases, and fluid phase plus 1 is question mark, because we don't know whether it was a fluid present or a fluid absent situation. So we don't see H2O, we will keep it as 5. Right? So you have 6 component system, 5 phases. So if we now do the variance diagram, variance calculation, C minus P plus 2. So you have 6 minus 5 plus 2 is equal to variance is 3. So in a temperature pressure diagram, if you have this line, now this shows that at isothermal isobaric condition there is only one variable. What is the variable here? Because all phases here are all phases are variable. So there is one variable in the equation. And remember, here we have neglected a very important term, which is FEO. If you take FEO and add it here, then it should be plus 1. But you will not increase the number of phases. So what will happen? This will be 6 plus 1 minus 5 plus 2 is equal to 3. So now 3 plus 1, you should have total 4 degrees of freedom. That means these are not univariate lines. These are not univariate lines. These are actually more than univariate. These are bivariate lines. So all these lines that I have drawn, they have more than one variance. That is why in the metamorphic phases diagram, pH2O is taken as equal to P total. Remember, in the metamorphic phases diagram, pH2 is equal to taken as P total. If you take this, then XH2O is equal to 1. If XH2O is 1, then the number of phases increases by 1. So the number of phases increases by 1, which means the degree of variance goes down to 3 again. Because they assume in the variance diagram, pH2 is equal to P total. Right? If it's pH2 is equal to P total, then XH2 is equal to 1. That means it was a fluid phase. So instead of the phases being 5 mineral phases, now you have one more fluid phase. So you have 6 phases in the phases diagram. And the components are 6 plus 1 at least, because you have Na2O, NGO, FUL, 2O3, FIO, so there should be at least 7 phases. So you have 6 phases. And therefore your F value, I will repeat again what I did because it's a little clumsy here. So number of cross components 7, phases 6, including H2 as a phase, plus 2, and this is the variance is 3. So in a pressure temperature diagram, so out of these 3, 2 are pressure and temperature. So if you assign the pressure and temperature, you still have one more variable to deal with. One more variable to deal with. And that variable is the mg by Fe ratio. So all those razor-sharp boundaries that are shown in the metamorphic phases, they are not univariate boundaries. They are bivariant or more. If I bring in potassium here, because hornblende contains potassium, then there will be an increase of phases. So all this makes these diagrams that I have drawn, the metamorphic phases diagrams, they are merely suggestive. They are not the final diagrams that you get. These are only as a first step. So why is it needed then if it doesn't have a value? Say for example, you say, I went to the field and I saw, and the terrain was green schist phases. So immediately when you say green schist phases, you have certain mineral assemblages in mind. And if you go and say, I went to a granulite phases terrain, then you already have a mental aspect. Okay, granulite phases means these could be possible mineral assemblages. Images flash in your mind. But if you say, I went to a metamorphic terrain, I don't know the phases. Now there you go. The person who is talking to doesn't even know what you're talking about. Do you understand? That is the most important thing. That is the use of metamorphic phases variable. It gives the listener or the worker a first order information of possible pressure temperature conditions. Beyond that, metamorphic phases principle does not have any numerical existence. The only way you can do it is find out the pressure temperature condition. So when you say green schist phases rock metamorphosed at 480 plus minus 3 kilobars or 4 kilobars, that's when you know, okay, so I know it, it's green schist phases. 4 kilobars, possibly garnet I will have. I might have a little bit of garnet in my kashish, small garnets, not big ones. Or if you have epidote amphibolite fasces, and say, okay, epidote amphibolite fasces, if I get mafic rocks, then I will get 2 amphibole assemblages. If there are high temperatures, I will get garnet. So you can start thinking of certain assemblages. So metamorphic fasces principle is a good first order discrimination diagram. Very first order discrimination diagram. But beyond that, it does not have a lot of numerical value to the metamorphic fasces diagram. And remember, one of the greatest lacuna of the metamorphic fasces diagram is pH2 is equal to P total. This is almost never works because all numerical calculations show that at high metamorphic rates like amphibolite fasces or granulite fasces or even epidote amphibolite fasces, where numerical calculations have been done and fluid characterization has been made, nowhere is it fluid present metamorphism. They just don't add up to 1. So this adding up to 1, assuming the fluid was a phase, is a complete nonsense. You see, if you reduce that, then the variance also increases. So all these boundaries in between fasces boundaries or fasces defining boundaries, these are very, very vague. But it gives you a first order impression of what you would like to expect in your rock. That's all about it. Nothing beyond. There is another little problem here in this diagram. This is hornblende plus quartz breaking down to 2-pyroxene plus plagioclase assemblages. There are more complications here, and I would like to tell you about it. So the reaction here is, leaving aside the problems, hornblende plus quartz is equal to 2-pyroxene plus plagioclase plus H2O. This is the reaction. Hornblende plus quartz is equal to 2-pyroxene plus plagioclase plus H2O. That's the diagram. And you know, hornblende can be broken up and you can do a much better characterization of the whole thing. Now, in this diagram, this reaction, this is temperature and this is pressure. And although, like all the reaction curves, they have a boundary like this, where there is hornblende quartz and 2-pyroxene plagioclase assemblages. This is your granulite fasces assemblage, and this is your amphibolite fasces assemblage. This is amphibolite and this is granulite. Within 2-pyroxene, you have of course orthopyroxene. Now, here I write plus H2. Say, for example, if the XH2 is reduced, XH2O is reduced. Have you understood? So what will happen if XH2O is reduced? That means if the mole fraction becomes progressively less than 1, then this reaction curve will start moving to the low temperature form. So XH2O is 1.0, 0.8, 0.6, 0.5, and so on. So what is happening if your rock is dry? If your rock becomes dry, that means you take out your H2O. You see what you do? You expand the granulite field to lower temperature. Do you see this? This boundary, hornblende plus quartz, shifts to the lower temperature. So the more anhydrous your rock is, the granulite fasces assemblages are stabilized at lower temperatures. Have you understood? They are stabilized at lower and lower temperatures. Now, this is a slightly difficult. if I take quartz in a rock, if there is quartz, then activity of SiO2 in quartz is equal to 1. But if the rock does not contain quartz, if the rock does not contain quartz, then activity of SiO2 in quartz is less than 1. So if you do that, so if this is hornblende plus quartz and you reduce the activity of quartz, then what will happen? This reaction will shift to the right. Just the opposite of what H2O did. So if you reduce reduce activity of SiO2, the amphibolite facies assemblage will move to the right. The boundary will move to the right. That means amphibolite facies assemblage would be stable at higher temperatures in silica under saturated rock. In silica under saturated rock, hornblende will be stable till higher temperature. Or hornblende will break down to 2-peroxide assemblages, 2-peroxide plus plagioclase assemblages at higher temperature. So here we go. If you have silica under saturated conditions, silica under saturated conditions, then silica under saturated conditions, then amphibolites are stable to stable at higher temperature for silica under saturation. And for H2O under saturation, amphibolites are stable at lower temperature. Do you see? So, H2O under saturation draws granulite to be stable at low temperature. Silica under saturation does just the opposite. So, the boundary between the granulite facies and the amphibolite facies, they are controlled by the under saturation with respect to SiO2 and H2O, and they affect the rock in opposite ways. This is also not taken into account in the metamorphic facies diagram, because in the metamorphic facies diagram you always contain quartz. You never consider activity of SiO2 as less than 1. It does not happen. Say, for example, in olivine tholeiites, in the normal moths, quartz is absent. Although there are certain other moths where quartz tholeiites, when you start already with higher SiO2 contents. So the SiO2 content of the rock and the H2O content in the rock largely determines amphibolite facies, granulite facies transition. This is a very, very important issue. So, for example, say for example, in the field, I don't know if you're proficient in the field, you will see that there are mafic budines in the field within quartzo-feldspathic rocks. You will have mafic budines within quartzo-feldspathic rocks. These are the mafic budines. They are very competent. So obviously they are budinars during deformation in the rock. Now you will commonly see here at the margins, you can see at the margins SiO2 is saturated. Have you understand? SiO2 is saturated at the margins of these budines because alongside you have quartzo-feldspathic rocks. Whereas the interior parts, these are silica undersaturated. Have you understood? these parts are silica undersaturated. Let's assume they are silica undersaturated. Therefore, at the margins, they are silica saturated. So, if I take this diagram, now the pressure temperature condition across such small distances are not likely to change very much unless the boundaries are related by thrusting. When the Boudinaging goes out of the, you can throw it out of the window. So in that case, if we look at the diagram, if I just consider silica saturation, then, you see this is silica. If there is high silica, the reaction will shift to the left. If there is low silica, the reaction will move to the left. Now see, if I take a pressure temperature condition here, this is pressure. If I take a pressure temperature condition here, then you see these parts where they have direct access to quartz, that means there is silica saturation, this curve is valid. But if I take the interior parts where the silica saturation is not so strong, this reaction curve will move away. This is for silica undersaturated and this is for silica saturated. So what will happen at the margins? What will you get? Hornblende quartz, but also 2-pyroxene plagioclase assemblages. You will get. So you will get granulite facies assemblages at the margins of these puddings. But in the interior portion, you will not see any pyroxenes. You will not see any pyroxenes. Why? Because at this part, silica undersaturation, Hornblende stability field has moved to the right of the pressure temperature diagram. So you will not see any 2-pyroxene plagiogranulite facies. So you will see amphiboles. Now if you just take this amphibole and this 2-pyroxene assemblages on the face value, you will say, oh, there is a very large change of pressure temperature condition. Why? Because 2-pyroxene is a granulite facies, Hornblende is an amphibolite facies, so the pressure temperature condition must be different. No, it's a role of silica. The pressure temperature condition is the same. So sometimes it happens, as the Boudinaging happens, sometimes there are cracks in these. And along these cracks, melts migrate along these cracks. When they migrate along these cracks, the margins of this also develop 2-pyroxene plus plagioclase assemblages. It's for the same reason. Sometimes during the Boudinaging there are cracks. You know, you have the parallel to the extension fields, etc. You develop cracks. So if you develop cracks, the melts that are formed, they migrate on this side. And around that, again 2-pyroxene assemblages are stabilized. But those places that have not been traversed by this granitic melt, the 2-pyroxene assemblages don't stabilize. So just by looking at the assemblages, do not infer about pressure temperature conditions. Do not infer about the pressure temperature conditions. Pressure temperature conditions, if you want to infer, you have to do it from quantitative thermobarometry, which I have talked before. Just because a mineral is not present and another mineral is present does not mean that the pressure temperature condition is a variable. It only means that there could be pressure temperature variation, yes, but other factors has to be eliminated first before you make this judgment that there is a large scale pressure temperature condition. No, it doesn't work. I will continue with the amphibolites, but just I will give you a small little story. There is a famous reaction. This is not amphibolite facies. I just thought that I should tell you the story because it created a furor and it started from our country. So I think it's better. There is a famous reaction. The reaction is biotite plus quartz is equal to orthopyroxene plus K-feldspar plus H2O. This is a very famous reaction that operates in quartzo-feldspathic rock, not mafic rock. Biotite plus quartz is equal to orthopyroxene plus K-feldspar. This is taken as a typical granulite facies assemblage. Orthopyroxene K-feldspar is taken as a typical. This is a metamorphic orthopyroxene, not a magmatic orthopyroxene, a metamorphic orthopyroxene. So, orthopyroxene K-feldspar indicative of granulite facies, and biotite quartz, this assemblages can occur all through, but because muscovite is not here, therefore we can safely say that the assemblage was on the right hand side of the muscovite stability curve. So we have biotite plus quartz, which is the amphibolite facies, and you have the granulite orthopyroxene K-feldspar. Now, in this rock, if I draw a temperature pressure diagram, say this is my pressure temperature condition, PT condition of a particular rock. There is a very famous quarry in South India which was first discovered and reported by a very well-known field geologist by the name of Pichamuttu. He developed this, and he showed that there are biotite quartz, biotite plus quartz assemblages. There is garnet also, but for the moment we ignore the garnet. And there they had patches. They had patches. Not all the patches, I'm sure you are not going into the complications, where you get orthopyroxene, biotite, K-feldspar, and quartz. Biotite and K-feldspar. And there, so this occurrence of orthopyroxene is called charnokites. I will tell you what is a charnokite. There is a strong problem with charnokite. Charnokite was, in the classical sense of North American geology, is a granite which contains magmatic orthopyroxene. That is a charnokite. So your charnokite, the orthopyroxene, is a liquidous phase. Have you understood? It's a liquidous phase. So garnet, orthopyroxene bearing garnet is charnokite, and this is magmatic. So the charnokite name comes from this magmatic orthopyroxene. When this term came to Job Charnock, who took it to Madras, and then he had the Charnock tomb in Kolkata. In India, the term is used in a way where in a quartzo-feldspathic rock you have orthopyroxene. It is not important whether the orthopyroxene is magmatic or metamorphic. Here you see when biotite breaks down to orthopyroxene, this is a metamorphic orthopyroxene. It is not a magmatic orthopyroxene. A North American field geologist will never accept such an orthopyroxene bearing charnokite. There is nothing called a metamorphic charnokite. There is magmatic charnokite. But because the world over in India, adds numbers a lot. So what happens now, we are talking of two types of charnokites. One is called magmatic charnokite and one is called metamorphic charnokite. So this was some sort of a, a compromise solution. Magmatic charnokite and metamorphic charnokite. Here we are talking of a metamorphic charnokite. We are not talking of a magmatic charnokite, which should contain demonstrable orthopyroxene as a liquidous phase. Right. So this is a small outcrop, for example, a quarry face. I don't think the metamorphic temperatures were different. These are these metamorphic charnokites, if you would like to call them. These are metamorphic charnokites. They occur like this. how did this happen? That was the question. How did this happen? Now, say for example, if this is a graph where you have biotite, quartz, orthopyroxene, K-feldspar. Now you see, if this is your pressure temperature condition, then biotite and quartz should be stable. Orthopyroxene, K-feldspar is not supposed to be stable. Biotite plus quartz should be stable. But somehow, if you can shift the reaction to the left and bring you to this new position, then you see orthopyroxene K-feldspar crosses over the pressure temperature condition and you have orthopyroxene potash feldspar stable. So, the question is, how do you shift this curve to this position? Remember here H2O is high and here XH2O is low. So XH2O is high. As you dehydrate the rock, dehydrate it, you bring down the reaction, the position of the reaction to here. So your biotite plus quartz will break down to K-feldspar plus orthopyroxene. Orthopyroxene plus K-feldspar, it will break down. So this alignment and this formation was alluded to that, okay, there was influx of fluids, but that fluid had a lower H2O than that pervaded in the surrounding rock. If the whole rock was surrounded, flooded, then everything would have been charnocite. But no, fluids came into the rock along particular channels, structural channels. Along those channels, H2O was reduced. And that is why you get orthopyroxene plus K-feldspar here. Question is, how do you reduce XH2O? The way, there was a person, he's very, very famous, his name was Robert Newton. Robert Newton. There were other people with him, some of the Indians were Janardhan, Newton et al. They published a paper in Nature, and they said that, okay, what we can do is, from the mantle, when gases are coming up, you can take that gas, which is carbon dioxide rich, and if there are channel ways to channelize this CO2 rich fluids, they would displace the H2O and they could cause charnokitization. So it is called charnokites in the making. Charnokites in the making. So what essentially you do, you have the carbonic fluids from the mantle that you tap using some structural controls, and once you have the structural controls, then CO2 rich fluid will flush out H2O from the system. Once H2O is flushed out from the system, then the reaction curves move from this position to this position. And the moment it crosses over this pressure temperature condition, you start stabilizing charnokites in a rock which should not have contained charnokite in the first place. So that was his model, that lower crust is more charnokitic or granulitic is because of degassing of the mantle. That is the word that he chose. Degassing of the mantle. So the mantle degasses, releasing carbon dioxide. Carbon dioxide migrates along structural channel and reduces the fluxes, the H2O that is there, and you start getting charnokites. It was torn apart later on. This model, very, very simplified model, was completely torn apart across the world. But Newton was became a very famous person, because I think he deserves the praise, although he was proved to be wrong. He deserves the praise because he initiated this discussion that caught the imagination of the world. And so the credit of triggering this debate should go to Robert Newton. There is no denying it. So when I started my professional career, this was one thing that had split the world into two. Charnokites in the making. There was the opposite thing, that the whole thing was a Charnokite, and fluid fluxing broke the Charnokites. So essentially it was that the curve was like this, and then you hydrated it and pushed the curve across the pressure temperature condition. And so the question was, did Charnokites break or did Charnokites form? Breaking of the Charnokites or making of the Charnokite? That was the debate. The only problem to this, in many of these quarries, except in this quarry, in other quarries, this Charnokite patches has no structural controls. No structural controls at all. I've seen this type of quarries in many other parts of India. There was a lot of discussion. Nowadays no one discusses it because it has been proved by many people that this neither Charnokites in the making nor Charnokites in the breaking mattered. But the point is that this same thing can be applied also to granulitization. Have you understood? Granulitization of amphibolites. What do? You have a particular pressure temperature field, you flux it with CO2, H2O decreases, the H2O decreases, H2O fluxing occurs, so XH2O decreases. As the XH2O decreases, the granulite facies become stable at low temperature, so you can form granulites at the cost of amphibolites. Okay, I think I will stop here. We will continue in the next class.